as we work on this, we're just going to launch right into how to work these problems similar to how we did with proportions. Um, it's a pretty straightforward deal from here. We talked last video about how to determine dependence from independence and work through some examples. So that's going to come up here as well, and we'll talk about that in the two examples that we have. Um, but mainly this is going to look a whole lot like what we did with proportion, two sample proportion testing. We're going to swap in mu's for p's, but we're still going to have our, lots of A, B subscripts running around. Just like a one sample mean, we'll be using a t-test statistic. Um, but hopefully this all looks pretty straightforward. So there's not a lot of theory to talk about. It's just, hey, same sort of stuff we've been doing before, just now a slightly different example. So our null and alternatives look like so. We can have a two-tailed test, we can have a left-tailed test, we can have a right-tailed test. Um, as before, when we subscript these things, generically I'll use A and B here. You can use 1 and 2, or you can use the letters that make sense based on the context of the problem, whatever the two groups happen to be. For our conditions, the first one, same as always, we want to make sure that we have good sampling. Again, I cannot stress this enough. Ask yourself those 3 questions about the bias that we discussed in chapter 1. Does it have sampling bias? Does it have response bias? Does it have non-response bias? Just like in the previous section, we needed to make sure that we were doing the right type of test. In that test, it was we needed to make sure that the data were dependent. Here, we need to make sure the data are independent. Pretty straightforward ask there. And just like before we talked about this, we need the difference in the sample statistics to be um, normal or approximately normal. And again, as we said, you don't need to know the why of this, but as long as each one is normal, the difference is normal. So we can, when we say this statement that we need the differences to be exactly normal or the differences to be approximately normal between these statistics, again, as long as each piece is normal or approximately normal, it works. So we're basically just going to be doing what we did for one sample testing, but for each one. And you can crisscross them. It doesn't really matter. If you get to this one is exactly normal, but this one's approximately normal, that's fine, or vice versa. As long as you show each one is either exactly or approximately normal. So how do we do that? Again, just like before, we use that gated approach. We ask ourselves, is the initial distribution X normally distributed? If X is normally distributed, then X bar is normally distributed. If X sub B, so sorry, if X sub A is normally distributed, X bar sub A is normally distributed. If X sub B is normally distributed, X bar sub B is normally distributed, right? So again, we're just doing that gated approach. We start off with, do we have a normality from our original populations? If not, then we look for the central limit theorem to be applied, which again says as my sample size gets bigger, the distribution of those means gets more approximately normal. And just like before, we use the same cut points. If we don't know anything about the shape of X, what the initial data looks like, what the original population looks like, then we use 30 as our cut point. 30 is large enough, but if we have skewness, then we probably need more like 40, 50, 60, something like that. We need something bigger. If we don't have any skewness, we probably don't even need 30. Something like 20 would be sufficient. So the same thing you've heard me say over and over, except now we just have to apply it to both groups rather than just one group. And I hope you're seeing why I made the comment previously. You got to make sure you're good with the one sample stuff because everything else just built off of it. Because we're just applying the same stuff. So if you hopefully you were good with that. If you weren't, use this opportunity to shore up your one sample stuff because you're doing a lot of the same stuff. So use this as to assist you in that goal if need be. Our test statistic, as before, it's going to be a little bit wonky. It's not nearly as bad as the proportion problem though. It looks like this. It's still a value minus a mean divide by the standard deviation. As before, we're subtracting 0 basically as the mean because we're typically going to say is one mean greater than the other, is one mean different from the other, which means their difference would be 0. So we don't write that down because this is just this is our sample statistic that we're building off of, and then we would say minus whatever's in the null hypothesis. Well, the null hypothesis value would be 0 because the difference between the means we're assessing to be 0, right? Look at the top of the page, you can kind of see that, right? That if you were to do mu sub A minus mu sub B, it would be equal to 0 in the null. and then divide by a standard deviation. How we got this formula is complicated. It's not something that you need to worry about. This is just the way that we are going to calculate the standard deviation for this type of test. Now, of course, how do we get the degrees of freedom for this test? The formula that we're going to use is the smaller value between n sub a minus 1 and n sub b minus 1. So whatever your sample sizes are, take the smaller of the two, subtract from 1, and that's going to be our degrees of freedom. But I put a little asterisk here. There are other ways to calculate this. Okay, so if you run this test in a statistical software, if you look at different textbooks, different online guides, you might see different formulas for this. There's lots of different ways to calculate it based on what your goals are. You don't need to stress about that. You don't need to worry about it. I just don't want you to freak out if you've seen other ways or if you see other ways. There are different ways that are accepted by the statistical community. They all have their pros and cons. And the idea behind why one is better than the other has to do with weeds that we're not going to dive into in this course. Okay, we just chose the formula here that's the simplest for degrees of freedom. And that's just to say, if you have a sample size of 6 and a sample size of 8, take the smaller 6, do your minus 1 just like we did before, and your degrees of freedom will be 5. Other formulas get really complicated. They lead to decimals. That's not bad. It's another formula to plug into. And the gains that you get there, in our opinion here, aren't really worth worrying about in this course. They are gains that you would worry about potentially if you were to do some real research, involving a problem like this. You might see those other formulas, and then it might be worth it to dive down the rabbit hole, but we're not going to. Step 4, just as before, find the rejection region or p-value. It's a t-test, so just like we did before, pull out your t-table, go to Excel to find your t-critical value, go to Excel to find the p-value. Just like before, nothing different, same way we work our probability statements. And the last 2 steps, again, you're going to get tired of writing this out. It's the exact same thing. And I say it every time in these videos just because I want to make sure you hear it one more time, because this is something that you need to know like the back of your hand. If your test statistic falls in the rejection region and your p-value is less than alpha, you reject the null. If your test statistic does not fall in the rejection region, your p-value is greater than alpha, we fail to reject the null. If you reject the null, you conclude the alternative. If you fail to reject the null, you cannot conclude the alternative. So again, make sure you know that. It's how we wrap up every hypothesis test. No matter what's happening in the previous steps, we work to the end the same way.